Compared to the rest of my student years, the mornings of the last few months have been different. As I'm riding my bike through the forest on my way to the lab, I realize I've really been enjoying this. Going out in the cold, the little of it we've had so far, sometimes even in the rain, looking at the trees, the clouds and the sky as I see the sun appear on the horizon, it's very relaxing. It's not that I don't enjoy going with public transport, the cold, the sunrises and sunsets are still there, but it feels different. To be completely honest, the ugly grey buildings get pretty boring after a while. There isn't much detail to look at, just straight edges, no interesting geometry, nothing. It's pretty unfortunate that there can't be more trees around there, surely that would make things more lively. Suddenly my thoughts are disturbed by the sight of a slightly familiar shape in the facade. Maybe things aren't so bad after all. Fractal geometry is something I've been interested in for the last several years. When I was 15, I found out about it and promptly started making fractal art. Later, as I had become a little bit more familiar with the topic, I also started exploring the mathematics behind it and also looked into how fractals can be found in nature. By then, I was at the end of my secondary education and I had to write an essay on something. And I decided to make it about fractal architecture because, yeah, why not? I just read a little bit on the topic and I found it absolutely fascinating. Looking back, there's a lot of things I would change about my approach, but I can't really do that anymore. So let's revisit the topic in video form. Tangent 1. Fractal dimension. When it comes to the history of fractal geometry, even though Benoit Mandelbrot is often associated with it, there are a few people before him who did a lot of work on the mathematical concepts that are used to describe the matter. In particular, Felix Hausdorff, George Bulligand and Hermann Minowski helped to lay the groundwork for what we'll be looking at today. In this video we're going to explore fractal geometry by looking at what fractal geometry is, where it can be found, in which ways it can be applied in architecture and what that will help to improve. So, what are fractals? In order to answer that question, we're going to have to do a little bit of mathematics, but don't worry, it's not going to be too complicated. If you were to look up the definition of fractal right now, you would probably find something along the lines of a self-similar mathematical shape. But that's a colloquial definition. If you look into it a little bit more, you'll see there's more to it than just self-similarity. One of the defining qualities of fractals is their dimension, which can be a non-integer value. In other words, a value that can be between two whole numbers. But in order to get to that, we'll first have to talk about coastlines. Measuring a coastline can be a pretty daunting task. This is because coastlines, much like a lot of other things in nature, are very rough in shape. What I mean by that is that these shapes aren't easily defined by straight or smooth lines. Trying to do so will result in detail of the shape being lost. In order to show what I mean, let's measure the coastline of Iceland. To do that, we'll start off with a ruler of 124 pixels. As you can see, it doesn't exactly fit, nor is it able to capture the detail of the coastline. This took 3 rulers and a little bit, but for the sake of this example we'll round up. As you'll see later, this issue will become smaller and smaller. Next we'll use a ruler of half the size. As you can see, that gives a slight improvement. This time it takes 11 rulers. We'll halve the size again, and this time it takes 24 rulers. Finally we'll repeat that one more time, and this time it takes 65 rulers. Now we'll Take these measurements and multiply the number of rulers by the size of the rulers in pixels. And as you can see, as you make the rulers smaller, it allows you to make measurements that are way more precise, which results in a measurement of the coast that is larger than the measurement made with larger rulers. This kind of gives you an idea of what it means for a shape to be rough. And with that, we're not very far off from actually measuring the fractal dimension of the coastline, which we'll do by box counting. So let's get into that. To find the box counting dimension, we need two pieces of information: the scale factor and the number of boxes. The latter of which is quite easy to understand, but the scale factor requires a little clarification. Scale basically refers to the size of something within a set relative to that set, and how much magnification is needed for the object to equal the size of the set. Let's take the example with the rulers. You start off with a ruler which on its own has no scaling, but if we split the ruler in half, we'll end up with two pieces, and that is what the scale factor indicates. If we then take all the pieces and split them again, we'll end up with 4 pieces in total, which indicates the scale factor of 4. And you can keep going with this: 8, 16, 32, 46 and so on. Now this is only in one dimension. If we do this in 2 dimensions, we'll have to be a little bit more careful. Let's take a square and scale it down by a factor of 2. Doing this will make the sides half as long, but the surface will be reduced by 4. Side note, this is going to be relevant later on, so keep this in mind. Because we're now in the 2nd dimension, to find the scale factor we need to take the square root of the number of pieces you would need to make a square of the original size. So we've got 4 pieces, and taking the root of that will end up with 2. The same can be done with the 3rd dimension. Take a cube and scale it down by 2, and take the cube root of the number of pieces needed to build a complete cube again, which is 8, and the cube root of 8 is 2. This can be done with pretty much every integer dimension. The notation for that is r to the power of n, where n is the dimension and r is any Euclidean space. I'm sorry Maurits, your work is amazing, but we'll probably cover non-Euclidean spaces some other time. So let's estimate the fractal dimension of the coast of Iceland we used earlier. We'll start off with a grid size of 265 pixels. This is our starting scale. We'll then color all the boxes that have a little bit of coastline in them, and then we'll count the number of boxes, which in this case is 33 boxes. Okay, now let's do that again, but this time with a grid that has been scaled down by a factor of 2. In which case we'll get 87 boxes. And now with a scale factor of 4, which gives us 204 boxes. Then we'll do that again with a scale factor of 8, which gives us 460 boxes. And finally we'll repeat that with a scale factor of 16, which gives us 1053 boxes. Now let's take the log of these results and put them in a graph. This can't be done with the initial scale factor of 0, because trying to do so will result in an error, because there is no way to raise any base to a power and then end up with 0. So we'll just leave the 0 there as is. Once we've done that, we'll end up with a graph that looks like this. It gives us a nice linear graph, and look, there it is. The slope of the graph is the fractal dimension of the coastline. But this is only an estimation. If we wanted to know the fractal dimension more accurately, we would have to keep counting boxes to add more data points. But this isn't possible for 2 reasons. One is that it is practically impossible to keep increasing the scale forever, not just because of the limitations of our measuring techniques. Going down to atoms would be the limit for that, but even if we were able to continue to magnify, we would eventually, after 115 steps, arrive at the Planck length, which is the hard limit, practically speaking. The other caveat would be that if you were to keep going, you would eventually end up with a coastline that is infinitely long, which for a fractal is fine, but for a coastline, you can't really do much with that result. Which brings us to the definition of a fractal, which In addition to being self-similar is that fractals have roughness at every scale of resolution. In other words, roughness all the way down. That's another fractal fallacy for you. Now, if we look at how dimension is defined with integer values, in case of 2 dimensions it is the relation between the circumference and the surface of an object, and in case of 3 dimensions it is the relation between the surface area and the volume. If we look at the Sierpinski triangle, with every new iteration more surface area is taken away, but the circumference increases in total length. And with the Sierpinski pyramid, every iteration volume is taken away, but the surface area increases, which is a very useful property. To get an idea of how, let's have a look at some natural examples of fractals. Tangent 2. Nature. An obvious example would be trees, in which the geometry has different uses, some of which are pretty deliberate. First and foremost, in order for photosynthesis to happen efficiently, a tree needs to collect enough water with nutrients, carbon dioxide and sunlight. It does all of that by having a very large surface area, both above the ground and underground. In order to make this possible while still making it possible for the reactants and products to be moved around, the trunk splits up into a few branches and the branches split themselves up, and this continues for several iterations. It doesn't stop there though, it continues in the leaves as the veins continue to divide to use as much of the available surface of the leaves as possible. This is all for the supply of carbon dioxide and sunlight, but underground the water is supplied in the same way but through the roots, which also have a branching structure. And the roots also keep the tree from falling over. So one of the uses of these structures is logistics. And if we look a little bit further, we can also see that in blood vessel networks in the cardiovascular system. You can also see that in bronchia and nerves, which allows for the efficient distribution of resources and signals. And if we look a little bit further, we can even see this in geographic features as opposed to just in organisms, such as river deltas, tributaries and mountain ranges. So you might already know that, but what you might not know or might not have considered is that the fractal dimension of these things can be measured. Leaves tend to have a fractal dimension of 1.6 to 1.8, whereas the fractal dimension of trees can vary from 1.4 to 1.8. Something that might also be good to know is that these examples are what's called statistical fractals, which means they do have a fractal dimension, but they aren't necessarily perfectly self-similar, but have similar roughness across different scales. Trees are kind of a special case here, because the fractal dimension can actually vary depending on which scale you look at. And this does depend on how self-similar the tree is. Trees that are more self-similar tend to have a linearity that is closer to 1 than the ones that are less self-similar. Now, there are way more examples of fractals in nature I could go into, but those are beyond the scope of this video, so it's time that we actually look at how these things are applied in architecture. Tangent 3. Constructions. Just as branching allows for resources to be distributed over a large area, so does it allow for forces acting upon a construction to be distributed over a large area. As an example, steel cables are made out of steel wire wound into strands, which are then combined with other strands, with or without a core, which makes them somewhat more fail-safe, because as one wire breaks, the entire cable doesn't necessarily fail at once, and it also makes the cable more flexible. I mean, just imagine having to use a solid rod of metal instead of a cable. It's going to be extremely hard to bend, and as it bends multiple times, it'll become more and more brittle because of fatigue. Another example is the Eiffel Tower, which, in addition to kind of looking like the Sierpinski pyramid, also splits up parts of its construction to make it sturdy but lightweight, and it saves on building materials. There is a caveat to that, however, which is that structures like that are pretty difficult to build. Designing these things on a computer is quite easy, but then bringing them into the real world would be both very labor intensive and difficult to do through traditional means because of precision. Luckily, 3-dimensional printing is slowly becoming more efficient and people are able to experiment with it to create structures like this, which could help to make things more durable, but might also change how parts of society look in the long run. Tangent 4. Aesthetics. It surely would change the looks of society, but fractal geometry already appears throughout both historical and contemporary architecture. Especially common in Europe are cathedrals like Duomo di Milano, where it is applied in the overall structure, trefoils and the pillars on top. And in other places like temples and mosques, and even entire villages. Not just for functionality, but also for cultural or religious significance and for aesthetics. More recently, modern architects have taken this to apply it to structures like the airport of Mumbai or the Howrah Bridge in Kolkata. Again, not just for functionality, but also for the look of it. And just look at my YouTube channel. I've been exploring fractal art for a long time and put it into literally everything. Partly because I want to look tech savvy, even though it took a long time to put this video together, but also just because it looks really cool. But could these aesthetics have another purpose? Tangent 5. Stress relief. It turns out that, yeah, there is another purpose to it. Biophilia, or in other words the connection to nature, and biophilic design are quite well known at this point. It is a design where plants and trees are physically worked into the architecture to provide a soothing environment, and it really does. Not necessarily because people are physically closer to nature that way, but because it brings natural geometry into an environment that would otherwise be very static and lifeless. And it turns out that fractal geometry, in particular that of structures with a fractal dimension of 1.3 to 1.8, so-called mid-range fractals, are really relaxing to look at because of how we tend to process visual stimuli. So this could mean that in addition to being more efficient and aesthetically pleasing, fractal architecture might also contribute to stress reduction. See, that's why all my branding has fractals in it. It's all just to keep you here relaxed and distracted so you keep watching. Which, if you stuck around until this point, well done. Thank you very much for doing that. To end the video topic, I've made a little fractal animation that's hopefully relaxing to watch. Special thanks to Chillheimer for providing the music that will be playing along with it. And this video is also available in a 360 degrees version, which, if you're watching that, I would encourage you to look around a little bit. Some of you might have noticed that I've made a few changes to the channel. I'm going to divide it up into 2 sections. The green videos are the regular versions and the blue ones are the 360 degrees versions. It makes things a little bit more interesting as there is more for you to look at. It also contributes to the complexity of my content and it gives me more time to think about the next video topic. Because unlike now, the 360 degrees videos and the normal videos will be released separately. I've also just released the 360 degrees versions of my first 2 videos, so you can also look at those if you're interested. If you want to keep up to date with the videos I release on this channel, make sure you subscribe and ring the notification bell. Also, this rusty old machine is looking for a new name. If you've got a suggestion, make sure to put it in the comments below. Link to all the sources I used in this video are in the description. You can also find the titles of the music I've used. If you enjoyed the video, make sure to give it a like and share it around. And with that said, branch out into the unknown and stay relaxed.